Good morning. Welcome to Krishna's class. In this talk, last time I said that towards the end of the talk that in the next lecture on the Banach theorem. But on later thoughts, I thought that probably it may be worthwhile to give at least one talk, quotient space x by. Now X is a linear space over K. This is the assumption where K denotes R or C. Depending if it is R, then you say it's a real vector space, and if it is C, then you say it's a complex space. Now F from X to K is a linear map. Essentially, it's a linear transformation from one vector space into another, because K over K is a one-dimensional vector space. Then F is a linear function. Now this particular linear transformation, that is from X to the associated field, is given a special name, namely it's a linear function. Now they do play a very important role. That is why we consider them. Now, NF we designate by NF the set of all vectors in X which gets mapped to 0 by F. Now we'll look at make just one line remark on this. If F is a zero linear function, that means a linear function that maps every vector to 0, which is just all the properties of a linear function, then the null space is the whole of X, as it is obvious. But this is a trivial scenario, and that does not provide us with anything exactly. So we consider the other scenario, namely F is not equal to 0. Now, then what happens is NF is a proper subspace of X, for the simple reason that there exists Y. So NF is a proper subspace since there exists Y not equal to 0. F of Y so there is a vector that whole scalar multiples of that have this property such that F of Y is not right. That is the meaning of saying F is not. So it's a proper subspace in the following sense. And now the consequence of this is the following, that we have already addressed this problem, but I will immediately give you a proof of this. That means X can be written as a span of NF and a non-zero vector which does not get mapped to 0. Okay, that is a non-zero vector which is not in. Okay, so X turns out to definitely tells you something about X. Now this is easily proved. So the first thing is that now this is also called a maximal proper subspace. Is also called, as I was telling last time, it is a hyperspace. So it's a hyperspace, namely maximal, proper, I have said why, how, in what sense it is said. Now we will prove this. That's the first thing that we just give a very quick proof. Right? And this is the step is very important. Now, you take an arbitrary x belongs. Let not equal to 0. That means y does not belong to. Now this is assured. Existence of such vectors are assured. Okay. Now what more you have? Then x can be written of a unique vector in F and ky for a unique scalar so this is the statement that we can make. X can be written as the sum of a unique vector NF in NF and ky, that is k times y, for a unique scalar. Now we shall prove this. It's quite easy to. So x you can write as x minus set the first thing is let x prime denote x minus ky. For f of x prime and you know that fy is not equal to 0, not equal to 0. Therefore, we get that means x prime null space of and obviously the way in which we have split up this is equal to suppose how do you get that? X is also equal to where x double prime belongs to NF and A prime belongs to K. That means K prime minus K of Y. What do you have? X prime minus and K prime minus K belongs to Y belongs to NF if and only if K equal to K. So we infer that this belongs to NF, and if this also has to be in NF, then K prime equal to K. So what does this mean? This means two things. X is equal to X prime equal to X prime. That is the representation X as ky with with k. So this is a very interesting result associated with. Okay. You can see that this plays at the root of all the remaining analysis that. So that shows that every vector x can be written as a vector in NF plus a scalar times y. This y is the same. See, what I mean to say is this. Once you have chosen a y initially, then you don't change it. Okay? But the choice for y, there are several choice for y, and if you choose another y, there is going to be another representation. Okay? So once you fix y, mark. Now we'll get more information about this representation. So henceforth we will be always keeping this y fixed. The property of y is that f of not equal to 0. This is a consequence of our initial assumption that f is not equal to 0. What does this mean? This in turn means that proper subspace and a maximal proper subspace. It's a hyperspace. That is, x is equal to span of okay. If you have NF, that is a null space of F, then you can find another vector y which is not equal to 0 such that x can be written as span of NF and then it is also called a a hyperspace. Now let us look at one example. Our favorite example. So what is a linear function on what is a this is the first thing that okay. So I take let in fact this is the usual stuff that we use. Then let A2. So A1 and A2 be the images of E1 and E2 respectively under F. A1 and A2 are elements of now X belonging to this provides us with a coordinate system. When you say you take E1, E2 is the standard coordinate system that you have for R2, and the ordered pair x1, x2 is the point in R2 which represents the vector x that we have chosen. Okay, right. Now, where x1 and x2 are scalars. Okay, now we okay. Now what about fx? You know that f is linear, therefore this is equal to f of E2, and that's equal to A1 x1 plus A2. Okay, so this is what you have. So this is fx equal to so every linear functional on R2 is of the form A1 x1 plus A2 x2 with all these equations. Okay. Now what about null space of F is the set of all x in R2 such that f of x equals, and that is x belonging to R2 or I can write it as x1 this is equal to 0. So let us look at the geometry of this. So in R2, what is this? This is a, so passing through zero zero. Of course, clearly, see a1 square plus a2 square not equal to 0. a1 and a2 cannot be simultaneously 0, because if a1 and a2 are simultaneously 0, then f of e1 equal to 0, f of e2 equal to 0, and consequently f of x equal to 0 for every x. But we have assumed that f is not equal to 0. So this is a f not equal to 0. That is the result. So it's a line that passes through the origin. So this is of the form this is the usual analytical geometry. Let's call this. So every L represents every L passing through the origin represents a linear function. This we have already seen. So recall, I'll just I'm not going to repeat the arguments. Then where x is f such that m is equal to n of x. Okay, of course, here at this stage any kf also has the property so this is not unique. So what do you call this? Therefore, there are several linear functionals whose null space is given by M. So it doesn't fix the linear function uniquely. Okay, but suppose alpha. Then what do we have? Then we have any x belonging to x is equal to x prime plus a times y where k is unique, and so this is what we have earlier worked out. And therefore, what we have f of x equal to f of x prime is 0 plus k times f of y. So we take f of y is fixed as alpha. This is equal to alpha. Okay. So for any x, you can write fx in the form fx is equal to k alpha, where alpha is equal to f of y. So just in terms of the value we prescribe for f at y, f is determined at every point of x. Okay, so that is the story. Now we are looking for the structure of all these details we have worked out. Okay, now we will work out this. So the space first of all, we define some okay. Let us make some definitions. X plus n is the set of all x plus y such that I want to use y part of there is equal to y plus so y is fixed and nf is, of course, once f is given, f not equal to 0, nf is a proper subspace of x. So this is it. Now this is not a subspace. Unless, of course, y is equal to 0. But this is called the translator f. Now, from our experience of working in R2, From our experience of geometric insight, in R2, parallel to okay, let us see this in R2. Later we will see. See, it's not very clear whether it works in an abstract space, but see what it is. In R2, so let us take R. And then you see that I have just now done this. This is A1 x1 plus this is a line. Okay. Now you choose a vector y which is not in this. Okay. So choose a y does not belong to L. Okay. So y is also not equal to 0. Now what is going to be? Is intuitively a line parallel to L and passing through P. Its coordinates are y1, okay, right? This is y1. Right, let us see whether this is the intuitive picture that you have. So you are going to get a line parallel now. This is because suppose you take a typical element x of this, then x plus y, there is only one rule of addition for vectors, that is using parallelogram law. So this is equal to the diagram. So this is going to be, if this is x, then this is x plus. Now suppose x prime is a vector, then x prime plus y is again complete the parallelogram with sides y and x prime complete the parallelogram and then go for the diagonal. So this is again a point on this line. You see that likewise for any choice of x on this line, the corresponding point x plus y move on this line. Okay, and this is something of the form a1 equal to some constant, c not equal to 0. When c equal to 0, you get this. Okay, let us try to work it out. Prove it more analytically. An arbitrary then what we are looking for is this, that is y plus this is what we are looking for. So what is NF? NF, so this is equal to x y1 plus two such that so we are looking at this one. Okay, then what do you have? It's prime. Okay, so okay, right. So what you get? You get if x prime equal to x1 prime, x2 prime, then x prime belongs to NF implies A equal to 0. Therefore, what is going to be this? So for this one, what you will have? So we have a1 y1 plus x1 prime. This is equal to a2 a2. So for any x, you see this is going to be the if it is of this form. What does this mean? This implies here as it is. And this is a line to L and containing and y1 y2 belongs to this side. So this is actually L plus 1. This is the line L plus 1. Okay. So that is the scenario in R2. So we get a feeling. Now we have to prove this in general. Okay. So let me use this notation. Y plus NF, which is essentially so let us designate. Now the first thing that you prove is this. This is obvious. Okay. So this is obvious because every y can be written as 0 and 0 belongs to so this representation is okay. Now we do make some deeper observations. Now here you see that suppose you take y1 two elements y1 and y2 this example. two vectors. One is y, say y, another vector z. Okay. Then you see that if y minus z happens to be in L, then bracket y is the same as bracket z. Okay. Now the interesting shall prove that Z is joining. How do you prove that? So to prove this, first we prove that given y and z, if and only if y minus z belongs to okay. Let us prove this. Right? I mean, this is quite easy. See, what we are asserting is the following. That's easy to prove because so any x belonging to NF implies x is equal to y plus some x prime. Okay. Where x prime belongs to so also now y minus z belongs to n, which implies y minus z equal to some x double prime belonging to n. That is, y is equal to x double prime. Therefore, x prime, and this is equal to, but because each one of them belonging to NF, therefore this is this. NF is a subspace. Therefore, x is equal to sum x tilde what does this implies? This implies, where did we start? We started with an x. Okay, x belongs to what? That is x plus now interchange the role of y and z. You know that y minus z belongs to nf means z minus y belongs to nf. What do we get? We get z plus nf is contained in y plus so we have two results. One is and the other one is z plus nf is contained in this. Whenever so one part we have. Conversely, that's obvious. Okay, therefore we have that we have. Okay, otherwise suppose then we prove that is empty set. Okay. So how do you prove this? Suppose not. Subtracting. This is what do you get? Okay. Now x prime minus x double prime, and because each one of them belongs to x. Okay, but and these are independent spaces. Okay, so what does this mean? This means z line, right? Which is a contradiction. So, thus, what we have either or okay. Thus, this joins and this is what we have just in the case of R2. See, what happens is in R2, you just get back to the figure. What you have is this. This is R2. NF. This is NF, which is a line passing through the origin. Now, y is one vector. Then this is now z is another vector. Then this is also equal to NF plus 1. Okay, what does this mean? Z minus y belongs to, this means that Z minus y this is Z minus y. Z minus y now lies in, this is Z minus. Now suppose Z is not here. If Z is not here, say you have a Z1 which is not here, then Z1 minus y does not belong to this. So this is the space Z1 plus okay. So in that case Z1 is not equal to this is the scenario. So what happens is this whole space, this space is completely written as the union of parallel planes. Okay. The union of disjoint parallel translates of so you can argue this in another way. Okay, you can put the argument in another way. That then we say define y is related to z belongs to it. Now, what we prove is this is an equivalence for x, y, or x is, that is clear because x minus x is 0, which is in NF. This is reflexive. Then x is related to y. X minus y belongs to NF, implies minus of x minus y also belongs to NF. That is y minus x belongs to that is there. So this is symmetry. When you have x is related to y, this is easy to prove. This is transition. Therefore, what does it do? Thus, this is an equivalence relation. So, what do you have? So, what does an equivalence relation do? Equivalence relation partitions Now, these classes are so that's the breakup that. So it's into disjoint, although this is very deceptive. Okay, at the outset it doesn't appear to be disjoint, but you see that one can prove that it is disjoint, and that's the fascinating part of this, as it is clear in the case of R2. In R3, what will happen? Because you see that NF is going to be a plane passing through the object. Now, what are the parallel translates of this? Parallel translates of this are planes parallel to the given plane. Okay, right? So the whole space can be expressed as the disjoint union of these parallel planes. That's the breakup. Okay. Now this space, the space of these disjoint vectors is called the quotient. So x by n equal to so these are all parallel translates of n. Okay, where this is it. Now we prove that this is it. What is addition? and this is xy, this is alpha belongs to k, this is the definition of addition and scattering. Show that then this is well defined. The only problem is that, in this kind of arguments, what you have is that suppose all that you have to prove is, I will just take one. Why you ask this? This is box x plus box y. This is box x1 plus box y1. So if you have x equal to x1, y equal to y1, and then x plus y is one representation for the box x1 plus box x plus box y, then x1 plus y1 is another representation for the same. Are they the same? It's quite easy to see, because you see that x plus y, this element in this box is x plus y plus some z. So a typical element is of the form this is x1 plus z1, where z belongs to okay. Now you see that x is equal to, see, we already have, take it out. Now you see that similarly y is equal to therefore one prime, okay, where x1 prime therefore so irrespective of what representatives you use for the computation, you always get the same sum. Similarly, for the scalar multiplication, that I leave it as an exercise. So addition and scalar multiplication are well defined. Now verify that all properties required for so x by nf is now a vector space. Now the next question is, can you say anything about the dimension of this space? Here, taking the case, not a case. Okay. So here, one thing is certain. For any x belonging to x is equal to x prime plus k times y. Choose y initially where y does not belong to. So this is then x prime is unique. It's a unique scalar. It's equal to k. It's quite easy to show. Okay. When you take x here, x can be written as x prime plus ky. Okay. Therefore, this is an element of k. This is 2. So what you have is that each x the quotient space x by nf now this is quite easy to see that Okay, so what are the elements of this? That is the structure of. Okay. One of the consequences is that now you see that y is not equal. It's a one-dimensional space. It's a beautiful result. Okay, so this is a one-dimensional space. First we write the theorem. Shall write the theorem. So quotient space of dimension theorem. That's the thing. So this is the theorem. Thank you very much. So that gives the insight into the geometry. I would suggest one example. The example is, try to work out this on a plane passing through the origin. It is, so the form A1 So, thank you very much. So, that is the structural theorem for the quotient space, right? I thought I would do this because it's quite important. Thank you very much. I mean, in fact, one remark I want to make is this. Because when f is the zero linear functional, then f is equal to 0. So the quotient space will consist of only the zero element. Okay. So that's the remark about this. And one more thing I wanted to say. Yeah. Space. One can discuss a quotient space which may not be a proper which may not be a, the analysis goes in the same. So that's another remark. The discussion would go through in the same. For instance, in R3, suppose you take a line passing through the origin. It's a subspace, but it's not a maximal proper subspace. Okay. Now, what are the translates of this? Parallel translates of this. The parallel translates of this are all lines in R3 parallel to this line, and they form a two-dimensional subspace. Okay, right? They form a two-dimensional subspace. Here, the dimension of the quotient space x by nf is always equal to 1. That's why it is called a maximal proper subspace, so that you cannot have an extension for that. And okay, that's why NF has no proper extension possible other than the whole of X. So that is the situation. In that case, it's a one-dimensional. The quotient space is dimension. So the analysis goes along the same lines, except for this difference. And this is not an what you call a hyperspace. You don't call it a hyperspace. I mean, the word hyper comes in R2 to talk about lines parallel through the origin, or lines are called hyper, or the line through origin are called hyperline or hyperspace. And in R3, the hyperspace is all planes passing through them. In n-dimensional space, you take any n-1 dimensional subspace, it is a hyperspace. That's the meaning. So I think I'll stop here today, and then once again just revisit all those norms, etc., and make the space an non-linear space, and then talk about all the used norms and so on. Okay, and through that we'll come to the norm of the linear dimension. After that, we'll take up the unbalanced. Thank you very much.